because it's the only force acting on the potassium ion. And we want the size of the electric field. So the electric field will be MA over Q. It's a positive 1 ion. So they gave me the mass, 6.5 times 10 to the negative 23rd kilograms. The acceleration, 1.8 times 10 to the 6 meters per second squared, and Q, 1.6 times 10 to the negative 19th. So that's enough, right? For that one, keep going. Is there more to this one? No. So you could not do this if you didn't remember that a net force causes an acceleration. But I don't feel unreasonable asking that of you. On the other hand, don't take this to be mean. I didn't receive a question. I'm ready. Send me a question. Mr. Sheldon, I don't know where to get started. I'll go, did you set the net force equal to MA? Would that have helped you? And if that's not where if you're expecting to have to use Gauss's law in this one, not really. This one's more review than anything else. All right. What else? What other one would you like to see? Yes, ma'am. Sure. All right, so number 4. Let's read it real quick. It says a 10 centimeter long thin glass rod uniformly charged 11 nanocoulombs, and a 10 centimeter long thin plastic rod uniformly charged negative 11 nanocoulombs are placed side by side, 4.10 centimeter apart. All right. What are the electric field strengths at a distance 1 centimeter, 2 centimeters, and 3 centimeters from the glass rod along the line connecting the midpoints of the two rods? All right. I think this problem is suggesting that I could use the equation of a thin, long rod. So the difference is that there are 2 of them, one positively charged and one negatively charged. So let's say that this is the negative 11 nanocoulombs and this is the positive 11 nanocoulombs. They say that they are 4 centimeters apart. Is that right? 4.1. It's a ridiculous distance. 4.1 centimeters apart. And I'm supposed to look at a line connecting their midpoints. So a line connecting their midpoint, maybe there's a line connecting their midpoints. And I want to know at a distance 1, 2, and 3 from the glass rod. So that's the positively charged one. So we're looking at a distance of 1 centimeter and then 2 centimeters and 3 centimeters. All right. What is the electric field from an infinite line of charge? Do you remember? If not, do you have it in your notes? I bet it starts with lambda, and it's probably divided by something, probably with the whole pi epsilon kind of thing going on. Maybe the number 2, and maybe r. An infinite line of charge. That okay? Now, when I look at this point here, I suspect I'm getting 2 contributions to the electric field. The positive charge is pushing this way, and its contribution would be based on being 1 centimeter away from the rod, while I'm also going to have a contribution from the negative one also in this direction, but its contribution being 3.1 centimeters away. That seem okay? So kind of my expectation would be to say that there's 2 contributions to the electric field. The first, where R is 1 centimeter. I guess I could write that a little nicer for you guys, just 0.01. And then I'm just going to be adding the other contribution. But it is 3.1 centimeters away. Yes, sir?
So I tried doing it like that, but then when you submit it, it gives you feedback saying you can't treat it as an infinite line because you know the length of the rod. So instead you had to integrate in each end.
All right, so it's telling you can't treat it as an infinite rod?
Yeah.
Okay. Now, that then suggests you're going to need to know the electric field from a finite rod. But you don't have to prove it. You just have to use it. It's in the textbook. I did not provide it for you in class. We didn't finish that problem because I thought the math was too rough. So here's where there's a disconnect between what I would have expected the problem to have asked you to do and what the problem did ask you to do. So just, this is my failing. I would have expected you to say lambda was equal to Q over L and treat it that way. Clearly, mastering has this answer anticipated and wants you to use the finite rod instead. So we would need to look up the equation for the finite rod, which I don't have in the back of my mind. But I'm sure we could look up if we wanted to. Now, I'm just, again, sharing with you, I would have used the infinite line approximation to do this. We are going to be different, but as I've tried to stress in the actual, in class, the AP1 exam probably would not expect this. If you're asked to do this on the AP1 exam, they might ask you to set up the integral to find this. They would probably not ask you to execute that integral, just set it up, and then they would give you this formula and ask this question. Do you follow the difference there? They would want to know that you could set the integral up. They would not count on you to have the skill set or the time to do the integration in a 15-minute problem. But they may expect you then to apply this to a situation that you are given in order to calculate an instance of the electric field. So if given this formula, how many of you would be successful in calculating the electric field? It's not all of you, but it's a fair chunk. Now, this would be the hardest question on the exam. But there's going to be one of these on the exam. There will be an electrostatic, there'll be a circuit, and there'll be a Faraday. We know that going in. The only time that changes is they'll replace a Faraday with a magnetic field question. But there will be an electric field question on the exam. Will it be this difficult? I don't know. So this is question number 3. Now, given this question, I'm not sure what they want. So what's the electric field strength 10 centimeters from the wire? All right. This, multiple choice. If this problem appears on the exam, it's very likely to appear in the multiple choice, not in the FRQs, where you have a minute and a half to do the question. Okay? So, when I look at this problem, I'm thinking straight away, an infinite wire of charge. So that's suggesting that the electric field would be lambda over 2 pi epsilon naught r. And we know that it's 2600 when r is 5 centimeters. What kind of change are we making? R is going to twice as long, right? Twice as big. So our new situation is going to be lambda over 2 pi epsilon naught times 2 times 5. I'm writing it like this on purpose because if I factor out the 5, I get lambda over 2 pi epsilon naught times 5 times 1 over 2. All of this is 2600. So my answer's got to be half of it, 1300. That's all the time you have on the multiple choice anyways. That was a minute and a half. I timed it because I hit the start button right when I started talking about it. That was a minute and a half of work. However, this is not on the formula sheet. If you don't have it memorized, you can't do this problem. Except, at this point, you should. More discussion on this problem? Yes, sir. It's not 2.5, it's 2 times 5. They told us that we wanted to go out 10 centimeters. So, my expectation is this problem won't be presented in this way on the multiple choice. They'll tell you that you have an electric field of 2600 newtons per coulomb when you are a distance r away from the wire. And then they'll say you move out a distance 3r away from the wire and ask what the new electric field is. So they won't give you 5 and 10 centimeters. They'll give you a multiple of your position. Do you understand the difference? Does it change the work that you have to do here? Not really. What you should be looking at isn't that you went from 5 to 10. You should look to see by what factor this number became this number. There's other ways to do these ratio problems too. This is just one. It is also likely they'll ask the ratio comparison between 2 points. And you'll have to set this up as a fraction. All right. Yes, sir. Be getting to a reasonable understanding. Point charges have a decay of 1 over r squared. A line of charge has a decay of 1 over r. And a sheet of charge is constant. A constant uniform electric field. That's what we've seen. Yeah.
Can you go back to the last slide, please?
Yeah. Yeah, I mean, if we really look it out, the actual electric field for each of these, what you should memorize is Q over 4 pi epsilon naught times r squared. That's the electric field for a point charge. Just know it. That's Coulomb's law. That's on the equation sheet. You know, that is, or Coulomb's law is, get them in your head. The next one isn't. It's not going to say that lambda over 2 pi epsilon naught times r is for an electric field for an infinite line. You have to memorize that. And you don't have to, but you're unlikely to derive it. Gauss's law isn't long. Once you get used to using Gauss's law, you're going to see that this one is pretty cake. It's pretty straightforward. I mean, if you can see the pieces of it here when you split it up. You know, you'll see that 2 pi r is the circumference of whatever you're using for your Gaussian surface. Because it's a can. The last one, though, we use it a lot. And it's really worth holding into your mind. This is we got it right at the end of class period yesterday. It is the electric field from an infinite sheet. And I want you to know that these values for lambda and sigma, Q over L, Q over A. Yes, ma'am.